This is a schematic diagram of the rcpcd apparatus that is in use at both School of Mines and NREL, kind of a block diagram. It's a contactless technique where the sample sits on an insulating plate which is positioned relative to an antenna. The sample becomes part of a high Q resonant circuit. Changes in the sample conductivity are coupled through the antenna system to the detection system, and the outcome is a transient. In the case of pulse excitation, the outcome is a transient profile of carrier decay that is, after processing and conversion of the AC to a DC transient, we get a detailed decay of the carrier lifetime after pulse excitation. Next slide, please. Here's a circuit schematic, and it's basically the high Q circuit exists here in the block called antenna. The sample is compared with a reference impedance in the comparator circuit. The conductivity of sample is zeroed out, and then upon application of a pulse, we have additional conductivity, the photoconductivity, and that's compared with the reference conductivity. So it's basically a different circuit. That AC signal is converted to a DC signal by a mixer, standard RF mixer, and the outcome is a transient which reflects the lifetime of the minority carriers in the sample after pulsed excitation. Next. Here's the example of the power of this technique. This was done in collaboration with Dr. Ann Dillon at NREL a couple of years ago to show the sensitivity. To show the sensitivity of this technique. We had single-wall nanotube, carbon nanotubes in Nafion binder, and so there, the whole sample, the complex, the matrix, is coupled to the antenna system of the RCPCD system, and we see transient decay, and this shows different wavelengths. And this is just to illustrate the sensitivity of these. The conductivity is quite small here, and there's no contact, but we do see the photoconductive characteristics of these nanotubes. We don't understand them at this point, but there is a fairly long decay time associated with these. So this was to illustrate the sensitivity of this technique. The next slide was the same set of samples were done on our RCPCD at School of Mines, and this was with constant excitation intensity. So the sample up here is I think the 60% crystalline sample, and let me put in here that the response time of RCPCD is much smaller, longer than that for the other techniques. It's a sensitive process. We gain sensitivity, we lose time resolution. So we do not have the fast rise time that we have in microwave or the TMPCD. So that shows here. We see the rise time here is 10 or 20 nanoseconds or so, which is really the system rise time for RCPCD. And we looked at all three samples, and there are slight differences. Okay, so we go left, 1, 2, 3. This is the highest crystallinity sample. And we really don't see much difference here in the primary decay that we see here. Now, one of the other features that comes out of the photoconductive decay is that a constant energy flux, constant pulse intensity, the signal height is proportional to the carrier mobility. So I believe one of the things we do see here is a mobility variation, this being the most amorphous, this being the most crystalline, and we see that the signal intensity is increased by a good factor of 2 between those two. So I think that effect is quite real, that we see a higher mobility in the more crystalline sample than we see in the amorphous sample. That would be expected.